Hello and welcome to the next episode of Klingberg Wing Mark II development. I'm Rolf Klingberg, your host. Today I'm going to be talking about development and production of the D-tubes for the wing. Critical item, and I hope you come on along and watch the rest of the video and find out exactly how I made these. Welcome back. As you can see, I've removed the D-tube from the framework. This is the wingtip section. This section of the wing runs from the attachment point here, which is attaches where the winglet is, and it runs out. What you don't see here, what's not on here, is the final wingtip, which is a light ply core with balsa foam on it for final shape. So the overall length of this section of the wing is about 6 feet. And as you can see, it's a pretty typical ultralight aircraft or model airplane construction. It's spruce and plywood. I have carbon fiber cap strips here on the spar. It has some Dow 2-pound foam, 2 pound per cubic foot foam for the ribs. Trailing edge is carbon fiber over Airex foam with some little shear webs of Divinycell there. Turned out to not be my favorite answer. The left side I actually used basswood for the trailing edge, worked out much better. A lot cheaper, easier to make, less time. This was an interesting experiment, but I'll use it on this one panel. I wouldn't use it again. So now onto the D-tube. The D-tube provides essentially all of the torsional rigidity, torsional strength in the wing. The wing is designed such that all of the bending loads are carried in the spar caps. At least that's how the calculations are made. In other words, I build the spar caps such that they are strong enough in and of themselves to carry all the bending loads. Now the D-tube itself can actually carry 20 to 30% of the bending loads, but I don't include that in the calculations because I just keep it as a safety factor. I do calculate the D-tube though for carrying the torsional loads. Now, how this is basically constructed, let's say I have a little flat panel here. This is, I'm using the Textreme cloth on the inside. This is 12K toe, spread toe, carbon fiber cloth. Extremely high performance on this cloth, also extremely high cost. Fiberglass would cost you anywhere from $5 to $8 a yard. The Textreme is 10 times that cost. So very expensive, but also very high performance that you get out of it. Very high strength to weight ratio. And on the outside is some fiberglass, some 3-ounce fiberglass cloth. And it is really designed just to provide the aerodynamic surface. So how I've designed this is that all of the loads are carried on the inside skin. The carbon fiber carries all the loads, and the rest of this is used just to prevent local buckling of that carbon fiber skin. Now, the fiberglass does carry some of the loads. It'll carry a considerable amount of torsional load, but it is not calculated in on that. I use this just basically for the aerodynamic finish on the wing. Now, some aircraft that are built like this, they use a thicker foam, and they bring the outer layer and the inner layer together. They probably use carbon fiber on both layers, and they taper the foam and bring those two layers together and bond those layers to the cap strips. And that way they're using both the outer and the inner layer to carry the loads in the aircraft. To make this easy to build, I decided not to do that, and how this gets bonded on is just like you see here. The back edge is cut. The fiberglass is not attached to the carbon fiber directly, and it bonds on just like that. So you'd say, well, you're wasting the strength of the fiberglass, Raul, and that's partially true, but a lot of loads are transferred through the foam via shear. So you can, I've calculated such that I don't require that the fiberglass carry any loads, but it actually does, because those loads are getting transferred via shear. Now the inside of that, this D-tube, the core, is this very thin Air-X foam. I think this is like 1.2 millimeters thick. It's very flexible for going around the leading edge of the mold, and really nice stuff. Get this out of Germany, and great to work with. You'll see other aircraft, the Millennium, I think the Swift uses thin stuff like this, but Millennium and some other rigid wings actually use quite a bit thicker foam, and they use about the same thickness as the cloth that I use. There is an optimum ratio between the thickness of the skins and the thickness of the core, and for this type of structure, this is about optimum. Going to thicker foam really doesn't buy you much, and it adds a lot of weight. This stuff weighs 3 to 4 pounds per cubic foot, and if you double the thickness of this, you double the weight of the foam core. Doesn't sound like much, but over an entire wing, it's several pounds. So there's no reason to carrying several pounds of extra foam that you really don't need. So I use the very thin stuff. Now, as you may recall from other videos if you watched them, the intent of this aircraft is to have this be home buildable, where the average builder with average tools, nothing fancy, no CNC cutters, no lathes, no mills, can actually build this aircraft. So I developed the molding process for these D-tubes specifically for home builders. And it is done on a male mold. You can find other videos on my site about how this process is done. And here at the end of this video, you're going to see the whole process for making this D-tube. But I use molds just like you see back here. It is a 2 pound per cubic foot Dow styrofoam that's been hot wired to shape. And it's made oversized. I make all the parts oversized, and I size them to fit after the fact rather than trying to mold them to the exact size. And as you can see, I have layout lines on here where all the ribs go. It tells me where the cutoff lines are going to be so that I ensure that when I make the part, I make it plenty large enough. The mill molding process is advantageous in 2 ways. Number one, it's low cost. If you are only going to build one of these, you don't want to make fancy carbon fiber molds and steel frames that cost as much as the aircraft, and then you use them once and throw them away, or they become objects of art in your shop. These molds are cheap enough, $100, $150 for a pair of those, and you could justify throwing them away. Now I've covered this one with Kevlar scrim cloth, which was just a little experiment playing around with that. It makes a mold that's durable enough. You could probably pull 4 or 5 or 6 parts off of that before the mold is shot. But it used a lot of epoxy. The scrim cloth just soaks up a lot of epoxy. Kevlar was a little difficult to work with. If I was going to do this again, I'd use fiberglass scrim. Be a lot cheaper, easier to work with. Would still use a lot of epoxy. Adds quite a bit of cost, almost 50% add to the cost of the mold. My other mold, I'm using duct tape on the outside, right on top of the foam. Just put on strips of duct tape, line them up, and you'll see that in some other videos where I'm using that. It is less expensive, it's faster, and it works just fine. So if you're only going to make one of these, the duct tape's fine. If you're a club and you're going to make 3 or 4 of these, then you'd want to cover your mold in some type of composite material. What you're going to see here at the end of the video is the whole process of how this is laid up on that mold. I'm going to run it in fast forward. I hope you enjoy that. I'm going to talk a little bit, before we get to that, I'm going to talk a little bit more about how this part is trimmed and fit to the wing. Now, when this comes off the mold, it is not torsionally rigid. You can still twist it. It has the washout molded in it. That's needed for the final wing, but you could actually overcome that by binding it to the framework incorrectly. So this has to be jigged up a little to make sure that we're holding the proper washout and that it's aligned with the rest of the framework. The same is true of the wing frame itself. This was built on a jig with the appropriate washout in it, taper and sweep and all that. But let's see if I can hold this up so you can see it. It is not perfectly rigid torsionally. You can still twist on it. Now the torsion critical because that sets the washout in the wing, and the washout is critical for stability and control. So when I bond these two together, I'm going to have a temporary jig set up that holds the trailing edge at the appropriate twist angle, and such that, and I'll have ribs, a couple of ribs in the front here that hold the D-tube in the appropriate position so that we have the 5 degrees of washout that's needed in this section. How the wing actually works is there's, at the root end of this, there's actually 3 degrees of washout, and then there's an additional 5 going out to the tip, which makes a total of 8 degrees of washout in the entire wing. Since I developed this process for molding these D-tubes, I've only made about 4 or 5 of these. And I've had various levels of success. I've had one come out really, really nice. I've had ones that come out just horrible, the early ones. And I thought I had the process pretty much pinned down, and I do. But I had an interesting phenomena crop up on this one in that, and you can probably see it in the lighting, there's a fair amount of surface waviness in here, which I haven't experienced this much in the past. I think it was due to having too much resin in the cloth on the outer layer. If that cloth is too resin rich, the resin has nowhere to go because it's a male molding process. There's no bleeder or breather layer. There's a sheet of plastic over this, and the excess resin really, the only place it has to go is out this trailing edge, and there's not much that can get out that way. So if you're resin rich, you could end up with this waviness. That's, I think, the probable cause of this. However, it could have been the vacuum bag breather material that I was using, the cloth that I used. So when I make the left one, I'm going to use some different cloth, and I'm going to be a little more careful on the resin, measure it out ahead of time, make sure we're not using too much, and see if it comes out a little bit better that way. Now, this waviness is really just cosmetic. It certainly has no impact on the structural quality of this component. And people say, well, if you're making composite molded surfaces, shouldn't they be perfect and smooth and all that and be great for the aerodynamics? And hate to burst your bubble, but no, not really. The airfoils that I'm using on this particular aircraft are not laminar flow in any way at all. They're old NACA sections. They don't require a laminar boundary layer for their performance. In fact, the turbulent boundary layer starts right around here. So this waviness, really, no impact on that. If these were laminar airfoils, it'd be a big deal. And we'd want to have something much smoother. So part of the reason that I picked these airfoils is because I knew this male molding process would not give me a final surface finish of the quality that you want for a laminar flow airfoil. However, that said, laminar flow airfoils do not work out well on flying wings. You would think that that'd be a great thing to add to a flying wing, but they have a significant negative impact on damping in yaw and roll. I'm going to have a video in the future that explains that whole phenomena. I've tried the laminar flow airfoils. I know that other people have tried them, and they quickly back away from them because there are some issues in terms of stability and control that can be difficult to overcome. If I were to put laminar flow airfoils on this wing, the winglets would have to be 2 or 3 times the size they are now in order to damp out the yaw situation. So these older airfoils with a turbulent boundary layer provide much more damping and yaw, which is a plus for us. On the other side, it really just is a good synergistic solution with being a home-built aircraft. To expect the average home builder to build a wing that is of sufficient surface quality to keep the laminar flow over 60% of the airfoil is just a lot to ask. Would require some very nice molds, and they'd probably spend as much time making the molds as they did on the entire aircraft, which is not the point here. The point is be able to build this at home cost effectively and go out and fly an aircraft that has more performance than anybody else out there and do that for a small amount of money. Given all of the parameters driving this design, that's where we are right now. I'm not sure if I'm going to actually use this one on the final aircraft. I'm going to keep this as a spare. I'll probably make another one of these. It is perfectly usable as it is, and I might end up using it yet anyway. but I'm going to see how the left one goes. I'm going to make that today, and if it comes out better than this one, then I'll go ahead and make a second one of these. So let's see. We got the TechStream cloth on the outside, which you know of, the Arex foam in the middle. As you see, I'm using some unidirectional carbon fiber here on the leading edge, and you might think that that's for strength, you know, the drag loads and all that, but it's not. It doesn't really lend anything to torsional strength either, or bending. What this is impact resistance, like if you bump into a bush or a tree or a person perhaps, you don't immediately damage the leading edge of the wing, and this provides some extra stiffness in that regard. Let's see, what else can I tell you? Let's talk a little bit about how I align this with the framework and trim it to size. Now this component is made 1/2 inch, 3/4 of an inch oversized all the way around, and then we got to get it down to the right size. So how I do that, we have the framework here, and I've cut out templates at the near the root and at the tip that are exact to size. And as you can see, I've attached the tip template to the rib that was already here. There's a composite rib that's here, and I've attached the template so that it matches up perfectly with that outside shape, and that sets the washout angle and gets this nose portion of the template at the appropriate angle and position, and it's parallel with the rib, and it's got the right washout in it. So I have this taped on here temporarily, and that'll be removed when I do the final assembly. And I have a similar situation here at the other end. I have a nose rib here, which I've tack glued on with hot melt glue, and that is parallel to the rib, in line with that. And this will be removed and replaced with a carbon fiber nose rib. And these are used to align the D-tube itself to the spar, and then I can mark the cut lines. So as you saw in the opening of the video, I had the D-tube on here, and there's some painter's tape on here, and I slipped this in place so that it's tight to the templates and aligned this way with my alignment marks that I pulled off the mold of where it's supposed to line up with the ribs. And then I can mark on the inside here. I got some painter's tape on the inside. I can just run along the aft edge of the spar here and mark where my cut lines are, and I can do the same at the ends. Now, you'll note that the number 1 rib is not here at the root end, and that's because it has to have the 5-degree angle for the dihedral set on it. And so this end of the D-tube and the rib and all that is going to get aligned and cut after the D-tube is bonded in place. Now I'm actually going to cut the D-tube 1/8 of an inch shy of covering the full spar cap. I'm going to leave 1/8 of an inch out here for attaching the cap strips that are going to go on the ribs. All of these ribs will get basswood cap strips, and they need those cap strips because they're transferring loads from the surface into the D-tube, have to be securely bonded to the spar. Just butt gluing them to the back edge of the D-tube is not sufficient in this particular case because that D-tube skin is so thin. So I'm actually going to bond the cap strips to the spar itself. The loads from the cap strips are transferred into the spar and then into the D-tube that way. Okay, so I've brought up some other components here. This is the nose rib that's going to go out at the tip. It's a carbon fiber and Kevlar sandwich panel construction. Once I cut the end of the D-tube based on that template that's there, I know that that template is 3/16 of an inch thick, so I can then mount this inside the D-tube at the appropriate position so that it lines up with the other rib. That'll be quite easy to do. And then once this is bonded in place, I can do the final trim on it. I actually bond the ribs, the nose ribs, into the D-tube first before I bond the D-tube to the rest of the framework. There's a variety of reasons for that, but I think it's for this particular process, it gives the most secure bond. If you apply adhesive to the nose ribs first and then try to put the D-tube on, what happens is you never have the D-tube in the exact span-wise location when you go to slide it on because of the taper and sweep. it is difficult to eyeball that one, and you end up scraping all of the adhesive off of the rib by the time you get the D-tube in place, and you don't really get a good tight bond. So if you set these inside the D-tube first and then bond them, you get a much tighter bond to the D-tube. You can actually go see that whole process in an early video that I posted. I believe it's titled Test Section Assembly. And you'll actually see the process where I bond these ribs in to the D-tube first and then bond the D-tube onto the spar. Now, in this particular component of the aircraft, there's the leading edge tube. This goes on the inside of the D-tube here. This is going to get bonded in here like this, along with a couple of nose ribs. And just like I did in the for the test section of the wing, you can go watch that in the other video, put that back. And so this will be sitting at the front edge of the wing like this, actually a little bit over like this. This tape here is where it gets cut and joins together at the hinge line here, the joint line. This is a custom tube that I made. You can go see video on how I made this tube. It is thicker here at the joint and very thin out here, only one layer thick out here. This gets cut here. A small piece comes out of the center. That small piece that comes out of the center gets mounted in the winglet mount. And then there's a joiner tube that slides in and out of this. There'll be a short stub of it here in the middle. And when you slide the wing on, that slides into the tube and transfers the torsional loads. That transfers the torsional loads from the D-tube into the winglet mount and then to the main section of the wing. I'm experimenting with the wingtips with a different type of joining rod here. You see we have essentially a hinge type arrangement for the wing joiner. These were custom made. There'll be a video coming in the future on how I made these. The bushing inside here is carbon fiber, and that bushing was actually roll wrapped on this particular rod to have the appropriate size match. These are currently bonded on here, but I'm going to run one titanium bolt through each one just for security purposes, belt and suspenders approach. Length of this pin will be mounted on a cap, securing cap and cover on the winglet mount, and to join the wingtip panels on, it just slides in like this, and that cap gets secured to the winglet mount so that the pin cannot back out. There's a bottom here, can't go out the bottom, can't go out the top. We're good to go. Be very easy to mount the wing that way. Now, I neglected to speak earlier about, I talked about the surface roughness. Now, this is the outer layer of material that I use in the molding process. This is Mylar for making stencils. And for this particular D-tube, I used a, let's see, it was an 8 mil thick version of this. I've used this at 4 mils, 8 mils, 14 mils. On the larger D-tubes, I've used 14 mils quite successfully. 8 mil might be a little bit too thick, and or it might be causing other problems, causing that surface waviness. This was the tightest leading edge radius I've tried to do with this molding process. That was a bit challenging. This was the first D-tube that I made that actually has washout in it. That made it a little bit more challenging. And it's the first one that had sweep in it. Another little challenge. So overall, it was a significant leap from what I've made in the past to making this one, and some problems cropped up along the way. Let's see, there's probably one other thing I should talk about here. Let's see if we can grab that off the end. Oh, here we go. At the tip, the template at the tip was very easy to line because there's a tip rib there to help line it up. This nose rib had to cut the washout very accurately on it, 3-degree angle for the face that gets bonded to the spar. But I, of course, have the sheet that I cut the template out of, and that can be used to help align. You can set the template, let me rotate this a little bit, you can set the template on the foam rib that's already here, and then come in and say, oh, yeah, I'm pretty close. That gets you a reasonable estimate of, okay, I have approximately the right spot. And then before I mount the D-tube, I'll come back with some electronic levels and angle gauges to make sure that that is in the proper position when we bond it all together. Now the root rib that's not shown here, that's a composite sandwich panel also, because there's going to be a couple of fittings in it to help align with the winglet mount and the rest of the wing. But that's the gist of the situation. If you want to see how the D-tube actually gets bonded on to the spar, you go look at that video about assembling the test section of the wing. I hope you stick around and watch the rest of the video on the fast forward, and hope you found this useful, helpful information, and maybe you'll try this molding process yourself sometime. Took me a couple years to develop it and still perfecting it. And as I learn things as I go along, I'll transfer that information to you. So stick around, watch the rest of the video, and I wish you the best in all your flying endeavors. Please fly safe, and bye for now. Okay, come on over, Dave. Okay, here's what we're going to do today. We're going to mold the leading edge D-tube for the wingtip panels, about 5 foot long. We have a male mold here that's styrofoam with a scrim layer of Kevlar on it to give us a nice surface to mold on. We're going to work to the, we have to work outside the final part lines. This is the final part line here, and we have a final part line here, so we have to make sure that the materials extend beyond those part lines for final trim. Right now I'm using vacuum bagging material here. This is the Stretch-A-Line vacuum bagging material that we're going to pull tight and tape to the mold, and actually using it as a release layer and not the vacuum bag. So we're going to initially prep this by cutting this to size and stretching it tight over the mold. We don't need to put mold release on that because it's just designed to not stick to anything anywhere. So that's our mold, and we're going to wrap all the materials for the D-tube around the outside. Now what goes on the inside layer is this Texstream spread toe carbon fiber. And if you step a little that way, you'll be, it's laid up on the bias, as you can see. Colors are running this way, right, to take the torsional loads that are in the D-tube. Now, of course, it doesn't cover the full size of the piece, so we have these other pieces that we have to add on. At the end of the Texstream stuff, they have this like single layer pieces that stick out. So I've set this up so that we have a full overlap. The loose fringe here overlaps one of the full solid parts of the weaving, and the same on this side. You know, so we have a full overlap of strength there, so that we have we make sure that we have at least one full layer everywhere. In some spots on the seam we have two, and the same setup down at the extra piece at the other end. Now this goes on the inside of the D-tube, takes the bending and torsional loads in flight. The outside skin of the sandwich panel is really designed just for aerodynamics. It does add to the structural strength, but this is what really carries the loads. Now I've set the Texstream on peel ply material, a Dacron here, polyester, and we're going to wet out the cloth right on that peel ply. That peel ply will leave a rough surface for bonding later when I assemble the D-tube to the wing panel. So we're going to wet out here on the plastic sheet. What we have to make sure of, we're going to lift up the plastic sheet in halvesies and check the other side and make sure the resin's gone all the way through the peel ply. Okay. We don't want any dry spots. Right. Okay. Now, the Texstream, because it is such a tight weave, the way that this is, it takes a while for the resin to get through it. Now I found this new resin from Rhino, the guys that make the bed liners. They're selling this epoxy, and it's relatively low viscosity. Okay. And it's very hard and has great physical properties on it when it's cured. I like it, and it's about $20 a gallon cheaper than just about everything else that's out there. And out of $120, 20 bucks is significant. So fairly long cure on this. This is workable for up to 2 or 3 hours at 70 degrees or so. So we'll be able to wet this out and let it set for a while before we put it on the mold. No need to rush. Okay, so it does take a while to penetrate through, and I find that if you use a squeegee and rub really hard, you ruin these toes. You start to, as it softens up, you start to pull them apart, and that's a bad problem. So if we need to help it penetrate through, I have the epoxy roller like this. You know, you get pressure on these little rings that are on here, and that forces it through without lifting up the fibers. pure time, we can just let it sit there and soak through. And then we'll come back and maybe do a little rolling and a little bit more squeegee. We can flip it over completely and squeegee as hard as we want on the peel ply side, right? But then when you go back the other way, you got to peel it away from the plastic very carefully to not separate everything. And the best, if we do that, the best way to do it, if we were to flip this over and squeegee it out, to go back the other direction, it's best to just roll it up. Just get on one end, roll it, turn it over, and unroll it. And that way it doesn't come all apart. But we'll use this if we have to. Okay, so that's the inside layer. The peel ply will go up against the release material that's on the mold here. And we'll use some probably long straps of masking tape to hold it in place temporarily. The masking tape won't stick to the wet epoxy. We'll just take that off when we get ready for the foam core. Now, the foam core, we're using some 1/16 inch Airex foam today. This will barely go around the tight radius on the mold, but it will make it. If we were to take this and try to bend it around there now, we'd run the risk of cracking it. But once this is on a layer of fiberglass with some epoxy on it, it distributes the loads. It just keeps it from cracking. So we'll be applying this to the fiberglass that's going to be out on the back side of the outside molding material. In other words, we're going to do the outer layer on its molding plastic and then apply this to it. And we're going to squeegee this as tight as we can to that fiberglass layer. So that's the foam core. So what we have here for the outer molding surface is, this is some, what did I say earlier? This is 8mm. This is 8mm Mylar, which is actually stencil material. I got this from Amazon. And you can get large rolls of this as stencil material. It's not cheap, but it leaves a really nice finish on the outside. It's upside down right now. We're going to flip it over. I've just got it this way to flatten it out. And then we're going to take this 120 fiberglass here. It's a 120 style. It's a satin weave, so it's very pliable and very tight weave, so that there's no air gaps, no epoxy gaps. This is wonderful cloth. This is the outer surface of the D-tube, and this is pre-cut, and we're going to roll this out onto the Mylar on the other side and wet it out. Once again, we have to flip it over and check it and make sure that we don't have any voids. Because a void will be a rough spot on the outer surface in the wing, and I'd have to come back with body putty and clean it up. I don't want to have to do too much of that work. So we'll be double checking to make sure that we don't have any voids, that's completely filled with epoxy. Once this is completely filled with epoxy, we have no voids that's on here, then we're going to put the foam core material on it. And squeegee that out. And then the whole thing goes up on the mold, because this is going to have the carbon fiber on it. Then we're going to get this up on here. And actually, how we're going to do it is we're going to place the mold on one edge here, and we're going to roll the mold across the molding material, and then tape it to the mold. We hope. And we did this once before. We just haven't done one with this type of a leading edge. It's a little bit more of a challenge. If this plastic, if this Mylar is too stiff for going around the tight leading edge, I have lots of the fiberglass cloth, and I have some different types of molding material. And because we have a long pure time, we have hours to work with, we'll just do a second one of these and throw that one away. Try another one. Okay, so that's our plan.
Like a bird on a tree, I'm just sitting here. I got time, it's clear to see. From up here, the world seems small. We can sit together. It's so beautiful, you and me. We meant to be in the great outdoors. forever free. Sometimes you need to go and take a step back to see the truth around you. From a distance you can tell. You and me were meant to be in the great outdoors, forever free. You and me, meant to be in the great outdoors, forever